So hey guys, sorry I had to miss class, but thank you for your understanding. So hopefully we made it to this point in class on Tuesday. If not, this should be kind of a separate area. So you should be able to just start from here in your notes, and then we'll review. And then, if we did, then perfect. So I guess what we're going to be talking about today in this video is the application of the effective modulus method, which we mentioned in the previous sorry, I'm trying to figure out this camera again. Sorry, there it is. Okay. All right, so we had mentioned the effective modulus method before, so I want to show us an application of the effective modulus method. And what we're going to do is, I guess, essentially derive several different expressions that we'll be able to use in future examples. So this is the application of the effective modulus method. So first, we're going to look at an elastic case. So let's say that we have, this rectangular specimen with a point load P naught on it. So we're given different concrete and steel properties. So we have, the area, the modulus, and then we'll find the stress and strain in the concrete given the load PC. And we're going to assume that P naught is compressive, so all the expressions that we're going to derive are assuming that P naught is a compression load. So if you have tension, then you're obviously going to need to use a negative sign. So first we have the elastic case. So in the elastic case, we're going to use, I guess, the same three properties, equilibrium, compatibility, and constitutive laws, for each of the following cases. So this will be kind of our pattern moving through. So first, in the elastic with equilibrium, we know that our P naught, the load, equals our P from concrete plus our P from the steel. So if we substitute in our area of steel times stress in steel of concrete, and then area of steel times stress in steel, we can simplify it a little further. So compatibility will have the change in strain of the concrete equals the change in strain of the steel. So this will be epsilon C minus epsilon C naught equals S minus epsilon S naught. And we know that in this case these are both 0. So we'll just end up with our epsilon C equal to epsilon S. So then we'll have our constitutive laws. So these are just our Hooke's laws, our properties relating our stress to our strain. So stress equals strain times modulus. We're assuming linear elastic behavior. And we'll do the same for steel. So remember, if you have a more complex case or you're exiting the nonlinear ranges, then we need to take care of that in our constitutive relationships. So next we can rearrange and combine these expressions. So if we plug our constitutive laws into each other, and I guess if we simplify the constitutive laws for strain and plug them into our compatibility expression, we'll find that our C over EC equals FS over ES. So then we can simplify this further. We'll find that our FS equals ES over EC times FC. So this ES over EC is what we call the modular ratio. So this modular ratio we'll call eta, and this is just ES over EC. So then plugging in our eta value, we'll have our FS equals eta times FC. So next we can use this and plug it into our equilibrium expression, and we'll get our P naught equals AC FC plus AS eta FC. And then if we solve for FC, then we'll find our P naught over AC plus eta AS. So you can see here our stress is equal to our force divided by, this is a transformed area. And this expression is important. So this is for the elastic case. So remember, for the elastic case, in our eta, we use our EC and not our EC effective, which we'll use next. So next we're going to look at the creep under the applied load. So this, we have the same diagram as we had above, only in this case we're looking at the change in the behavior over time. So we're looking at the creep effects. So our equilibrium, we're going to have the same equilibrium expression. So we're going to have our P naught equals our concrete component plus our steel component, which will equal AC FC plus AS FS. Our compatibility will be the same. Delta EC equals delta ES. We'll have EC minus EC naught equals epsilon S minus epsilon S naught. We don't have any initial strains, so those are equal to 0. So once again we have our epsilon C equal to our epsilon S. Then we can move on to our constitutive relationships. So these will be the same. So we'll have, for concrete, will be FC equals our strain times our modulus, except in this case we're including creep effects, so we're going to use the effective modulus. And if you can remember back, by definition our effective modulus is just equal to our concrete modulus divided by 1 plus our creep coefficient. And then for steel, we're not going to take into account any relaxation, so we just have Fs equals Es times, or epsilon S times Es. If we were to take into account relaxation, we could take into account, or we could account for it in our constitutive relationship. All right, so then doing the same thing that we did above, we'll have equating our strains and using our constitutive rules. We have FC is over EC effective equals Fs over Es, which could be Es effective. And then this solving for Fs, we'll have Fs equals Es over EC effective, and this all times FC. So then once again we can define this as our effective modular ratio. So our effective modular ratio, which we'll call eta prime, is equal to Es over EC effective. And this is the effective modular ratio. So next we can use this the same way that we did before. So plug this in and we'll find that our Fs equals eta prime times Fc. And then we can plug this into our equilibrium expression. So we'll have P naught equals AC Fc plus As eta prime Fc. And then solving for Fc, we'll get P naught over AC plus eta prime AS. So this is our second expression, which accounts for the creep. And we can note that this entire lower expression then is our effective transformed area. So our transformed area accounting for creep effects. So if we were to look at an incremental load, so if we had an incremental load, delta P naught applied at time t sub I, then we could use the above expression, except now we would have an incremental stress equal to our incremental load applied at time ti over our AC plus eta prime from time ti to time t times AS. So this will be an important expression that we'll look at later, or we'll use later. All right, so next we want to know what the creep under the shrinkage-induced loads will be. So our shrinkage, so our specimen, so let's say we have an initial specimen, and it can just go on indefinitely in one direction. So we have an initial length for the specimen. So this will be initial. So the specimen's going to want to shrink some amount. And that shrinkage, so let's say this is how much it wants to shrink. So this shrinkage is going to be restrained by the steel. So what's going to happen is it's only going to shrink, maybe this much. So this is the amount of the actual shrinkage, or restrained shrinkage. So then what we'll say here is we'll define two other variables. So we'll have ECF, which is our restraining. It's the amount of stress that is, doesn't occur in the specimen because of the restraint of the steel. And then we'll have EC, which is the actual strain in the concrete. So then we can go to our same three expressions. So first, equilibrium. So nothing changes with equilibrium. We still have, P naught equals PC plus PS, which will equal AC FC plus AS FS. Since there's no applied load, this is going to equal 0. Next, we can come and look at our compatibility. So first we have our change in concrete strain equal to our change in steel strain. So we know that we don't have any initial strains. So, it's going to equal 0. So because it equals 0, we know that our EC is equal to ES. And then we know from our figure that our ES is, our EC equals ES is going to equal our epsilon SH of time, which is related to time, plus our ECF. So I have the signs right here. I guess it's because of the way we set up our sign convention as to why this expression is. You'll have to just trust me on this one. So then we'll have our constitutive laws. So our constitutive laws are the same as before. So we'll have our FC, sorry, equals epsilon CF times EC effective. And our EC effective, once again, is going to equal EC over 1 plus CT. Then we'll have, for steel, our FS equals ES epsilon S. Alright, so, and note that the sign for ECF in 2 is going to give you a negative value for tension. So the reason that we set up the sign value here is in this case is going to give a negative value for tension. Okay. So after we have our constitutive laws, we can start plugging everything into our equations again. So if we if we simplify for our strain in our constitutive expression, so here we can have our ECF, so our epsilon CF is equal to sorry, we're plugging in, okay, let's get rid of that. Alright, so our epsilon S is equal to Fs over Es for steel. And this equals our epsilon CF, which in this case, equals epsilon C, which equals our shrinkage of T plus epsilon CF, which in this case is our FC over EC effective. So I hope this made sense here. I was just substituting into some of the equations that we already derived above. Alright, so next we can simplify, and if we solve for Fs, we can find that our Fs is equal to Es times our epsilon shrinkage plus Es over EC effective times FC. So once again, you can see here we have our eta prime. That's a poor eta prime. Let's try again. So then we can plug in and solve for Fs. So Fs equals Es epsilon shrinkage of T plus eta prime Fc. And then if we solve for, or if we plug this into our equilibrium expression, we'll get, so plug into equilibrium, we'll get AC FC plus AS times all the expression above, ES epsilon SH plus eta prime FC, and this all equals 0 because we don't have any applied load. So if we solve for simplify and solve for FC, we'll find that our FC equals negative ES epsilon shrinkage times AS all over AC plus eta prime AS. So I hope you're starting to see a pattern in the denominator of all these expressions. We can see that down here we're always getting this effective transformed area. Which is going to make it really nice when we need to combine all these effects. Alright, and then if we want to include a point load, we can just, because stress is additive, we can just say, we have our effect from shrinkage plus just our point load. And if we want to look at the incremental strain then, incremental shrinkage strain effects. So let's say we have an incremental shrinkage applied at T sub I. Then what we'll have is we'll have our delta FC from Ti to T equals, so all we do like before is substitute in our shrinkage at time Ti times AS over AC plus eta prime from Ti to T times AS. So this we'll use later as well. So next we can look at the creep under prestressing, the prestressing force. So this is essentially the same procedure. So I'm going to try to run through it. So we have, if we have an initial position, after the prestressing occurs, it's going to cause an initial deformation here. So this is the initial, and this is the final after prestressing. So this change here, we say our EC is equal to our change in delta ES. So we don't have any applied load, so our equilibrium will have PC plus PS equals AC FC plus AS FS equals 0. Our compatibility will have the same thing. Our delta epsilon C equals delta epsilon S. In this case, we do have an initial delta. We do have an initial epsilon S. So this is now EC equals epsilon S minus epsilon S naught. So this initial is a result of the prestressing. Okay, and then our constitutive laws, they're the same as before. So our FC is equal to EC, or epsilon C, EC effective. Our EC effective is EC over 1 plus our creep coefficient, and our steel is equal to epsilon S ES. So then we can do our normal substitutions. So setting our strains equal to each other for steel and concrete, and plugging into our compatibility expressions we can find, we'll have, so simplifying, we'll have our FC over EC effective equals FS minus FS naught over ES. And we have this FS naught now because we have an initial prestress. So then we can solve for FC, or sorry, solve for Fs. So we'll get Fs equals Fs naught plus our eta prime times Fc. And then we can plug this into our equilibrium expression. So plug into the equilibrium, and we'll get AC FC plus AS, and now our Fs is our Fs naught plus our eta prime FC. And this will all equal 0 because we don't have any applied load. So then we can simplify and solve for our FC. And our FC is then equal to negative times our prestressing force times the area of steel over, you can see that we have the same denominator again. So this is really nice because now we can, it's all additive. So we can add this stress to the others if we have a prestressing force. And once again, we can take care of incremental prestressing the same. So let's say for an incremental prestress of delta Fs naught, applied at time t sub I, we'll have our delta Fc equals negative delta Fs naught As over AC plus eta prime Ti to T times As. So you have the same denominator again for the incremental force as well. All right, so this is the important expression, and the incremental one is if if you have multiple prestress effects. So next we're going to look at just kind of a general procedure for combined effects. So in this, I kind of lay out a couple steps that we can follow, and we'll look at them in a design example at the end. So first, we have to compute the time varying increments, incremental stress due to the shrinkage. So first, we're going to take into account shrinkage. So let's say we have some kind of shrinkage development. What we essentially do is we say that we break this shrinkage into smaller segments. So we say between Ti and T1 we have a certain amount of shrinkage, and we assume that we apply that shrinkage as a force on the structure. Then at time T2 you have an additional shrinkage, and you apply that to the structure. And then finally, at T3, you have another shrinkage value and apply it to the structure. So what this will do then is then we can calculate our incremental change in the stress as well from this. So and this would just be using expressions derived above. So we're going to make a simplifying assumption in our example. So when we get there, we can talk about that a little more. And you can see here we're just using the expressions that we derived above. So next we need to compute the. I'm recording a class.
Oh, sorry. I'll read it. Can I just I'll come back later.
Okay, so we have to compute the time varying concrete stress. due to the pre-stressing and the initial load. So we can say that we have, if we're in the case where we have a constant load applied and a constant pre-stress at the beginning, then we can just find our creep over time as shown below here. So you can see, in this case we're saying, we only have one load applied, one pre-stress applied, and it's all applied at T0. So this makes everything kind of simple for us. So next we want to compute the time varying increments of concrete stress due to any other incremental loads. So above we looked at the initial load, and here we're looking at any additional loads. So here we can separate them out using superposition and just say that if our stress at any time is going to equal the summation of the effects of the loads applied at other times. So if we have a load applied at T1 and another load applied at T2, we can account for them separately and then just add up the effects at the end. So here you can see would be the stress. So the initial stress and the stress decrease because of creep. The stress caused initially because of the force and then decrease because of creep. So these are all additive. So then finally at the end we can just use superposition and add up all of our concrete stresses to find our final stress in the concrete. So this is the elastic. This would be everything because of shrinkage, and then all our creep effects. So next we can use the concrete stress that we calculated to find our steel stress. So here we would find our stress in steel, which would just be our P minus our FC AC over our steel area, just from equilibrium. And then we can use that to find the the strain in our steel. So we can use that to find the strain in the steel and also the strain in the concrete. So next we're going to look at a couple example problems. The first is just a review. So this is the first step in all of our problems is always to calculate our shrinkage strain and our creep coefficients. So this is just an example to help us just revisit it. So I'm not going to go over this. You can go over it in your notes and on your time, and use it to kind of help you with the homework assignment. But you have all the information. So first you need to calculate your shrinkage coefficients, your ultimate shrinkage, your shrinkage at the time of interest, and then you can find your creep coefficients, and then you can use that to find your creep strains. All right, so this next problem is kind of the culmination of everything that we've been talking about so far. So in this problem, we have a structure. We're given this structure. It's a two-story structure with we have the casting order. So the lower level columns are cast first. Then we have the first level slab. So we have first these lower level columns are cast. Then 14 days later we have our slabs cast on top. So that'll put an initial load onto our lower level columns. So then 14 days after that, we're going to have our next level columns cast. And then 14 days after that, which I think I'm out of colors, maybe we'll try a highlighter. But 14 days after that, our top slab is going to be cast. And this is going to put an additional load on our structure. So what we're asked to find the deformations at 6 months after casting. So find the deformations at 6 months after casting in the first story center column. So we're looking at the first story, so we're looking at this column, and we're looking at the center column, so we're looking there. So using that, we can say, well, what's our tributary area? So we can find our loading, and we know that this column is going to see the load of the slab, the columns, and the upper slab. I think in this problem we're going to simplify things and say that the column above the center column is going to be negligible, just to kind of simplify our lives. But if you wanted to be exact, then you could include that effect as well. We're given that it's grade 60 steel. We're given that the concrete strength is 4,000 psi. It's a 7-day moist cured concrete, so all the specimen are 7-day moist cured. We're given that we're not given any humidity information, so that means we'll need to assume worst case. So we'll assume that our relative humidity factor is just equal to 1. And so the shrinkage, and the forms are removed 7 days after, so our shrinkage is going to be considered at 7 days. And then finally, we're not given any information on the concrete mix, and this is typical. So we're not going to be able to reduce anything because of favorable concrete conditions. All right, so our solution now. All right, so our first step is we want to calculate our shrinkage strain. And in order to do this is kind of the simple part. We just need to find all of our factors. So you can look back in your notes, but our curing factor is going to be 1.0 in this case for a 7-day moist cure. For relative humidity, no information is given, so this is just going to be 1. Our volume to surface area ratio, we're going to simplify it and just say our volume is equal to our area. So volume to surface area equals, we were given 15-inch square columns, and our surface area then is just 4 faces times 15 inches. And this will be 3.75 inches. So then we can plug this into our volume to surface area factor. So 1.2 e to the negative 0.12 times 3.75, and we'll get 0.765. So then we can calculate, we don't know any other information, so we can calculate our ultimate shrinkage. And if we just take all the factors times each other times, so 780 times all our shrinkage factors, and this is in micro strain, what we'll get is 597 microstrain. So then our time factor, so we're concerned with 6 months. So we want 6 months. So we'll use our time factor, so we'll have so it's T over 35 plus T because it's moist cured times our ultimate. So this will be 6 months times about 30 days in a month minus 7 days, which is the time after we consider shrinkage. And this is all over 35 plus 6 times 30 minus 7. And this is all times our 597 times 10 to the negative 6. So what we'll find then is our shrinkage at 6 months is 497 times 10 to the negative 6. Alright, so now that we have our shrinkage strain, now we can calculate our creep coefficients. So our next step is calculate required creep coefficients. We're going to need a few of them. Okay, so first our loading age factor. So loading age equals 1.25 times the time when our loading age is applied to the negative 0.118. So this is going to depend on the load, so we can't calculate one factor, because different loads are applied at different times. Relative humidity, no data is given, so we have our relative humidity factor equal to 1.0. And then our volume to surface area ratio, we can plug into our expression. So for creep, we have a different expression than shrinkage, so 2/3 times 1 plus 1.13 e to the negative 0.54 times our volume to surface area ratio, which was 3.75 inches. And this is going to give us a factor of 0.766. Alright, so we need the we need the creep coefficient for the loading due to the first and second floor slabs. For loading due to first and second floor slabs. So we can set up a table. Alright, so we'll have load, time of loading, final concrete age, and then time after load application, then we can find our loading age factor, we can find our creep coefficient, and we can find our ultimate creep coefficient, and then we can find our time, or I guess, and then we'll just find our time dependent factor, which will equal t to the 0.6 over 10 plus t to the 0.6 times our ultimate. Okay. Alright, so we're concerned with two loads then as well. So load 1 and load 2. So load from the first and second story slabs. So the first one is applied 21 days after the initial forms are removed, and the next is 42 days. So, and then the final concrete ages are both 6 months, so just half a year. And then the time after the load application is just our final concrete age minus the time of the initial load application. So the first will be 162 days, and these are all in days, and the last 139. So then we can find our load age factor. So our load age factor is will be 0.873, and this is just using our time of load application. And then for the second one, we'll have a 0.804. And then our ultimate creep is going to be 2.35 times our loading age factor, and then times our volume to surface area ratio factor. So this will be 1.57 and 1.45. So then plugging in our T, which is the time after load application, we'll have a 1.07 and 0.955 will be our two creep factors that we'll use. Okay, so next we need to find our modular ratios. We need to find all our concrete properties and then also our deformations. So we're going to calculate deformations that occur due to the first floor slab cast. Okay, so first we can find our concrete modulus. So our modulus of elasticity is just 57,000 times square root of f prime c, which was 4,000. And this will be 3,605 KSI. Then we can find our effective modular ratio. So we'll call this E effective 1 because it's going to be our first load stage. So we'll have EC over 1 plus C, we'll say C1. So this will be 3605 over 1 plus 1.07. So this was from our table here. And this is 1742 KSI. So next what we can do is we can find our effective modular ratio, which is ES over EC effective 1. And this will be 16.6. And then we can find our transformed area. And this will be, we'll call it ATR1. And this is equal to AC. So our AC plus 801 times, we said, I think, a 2% reinforcement, so 0.02 times AG. So then we'll have our ATR is going to equal our AG times 1 plus 801 prime minus 1 times 2%. And this is just saying that AC equals AG minus AS. Okay, and then plugging in our numbers, we have 15 square inches times 1 plus 16.6 minus 1 times 0.02, and this will give us a transformed area of 295.2 inches squared. So next we can use this, or we need to find our applied axial load. So our applied axial load is our tributary area, 20 feet times 30 feet, times our slab thickness, 10 inches, over 12 inches per foot, and then times 150 pounds per cubic foot for the density of concrete. So this is our tributary area. And if we run the numbers here, we'll get this equals 75 kips. So then we'll find our concrete stress. So our initial stress, FC1 at 6 months, is just going to equal our P1 over our transformed area. And this will be 0.254 KSI. And our concrete strain then epsilon C1 6 months is equal to FC1 over EC effective 1. So this will be 146 microstrain. And then our steel stress is just going to be our eta 1 prime times our FC1, and this is going to be 4.22 KSI. So next what we're going to do is similarly for the second floor. So calculate deformations due to the second floor slab. Okay, so basically the same thing. So first we need to find our EC effective 2. So this is just our EC over 1 plus C2. So our 3605 KSI over 1 plus 0.955, and this will give us 1844 KSI. So we can find our eta prime 2. So our eta prime 2 is once again just ES over EC effective 2, and this will be 15.7, so a little less. And then we can find our transformed area. So I'm not going to go through the same, So our A transformed 2 is just going to be, just like above. We'll have AC plus eta 2 times our 2% steel. And this will be just, the same calculation as above, and we'll get 291.2 square inches. And you can look above if you need to. Okay, so then we'll find our applied axial load, once again using the same tributary area, so 20 feet times 30 feet, times our slab thickness, which is different here. We have an 8-inch slab, times 12 inches per foot, times, once again, we're going to say we have the same concrete density. And here we'll get 60 kips. So then we can find our concrete stress, and so FC2 at 6 months is just our P2 over our A transformed 2. So this will be 60 kips over our 291.2 square inches. and this is 0.0206 KSI. So then we'll have our concrete strain. So our EC2 6 months, and this is our FC2 over EC effective 2, and this will just be 112 microstrain. And then our steel stress. And our steel stress FS2 6 months is equal to our eta 2 prime times our FC2, which is going to equal 3.23 KSI. Alright, so we're almost there. So we have the last step before we can add all our stresses together. So the last step here will be calculate the creep from the shrinkage strain. So we need to calculate creep from shrinkage strain. So this is where we're going to make that approximation that we said before. So we're going to say, so what we'll say is we'll assume shrinkage occurs early. So we're going to assume 1/3 of the 6-month shrinkage will be used for the creep loading. So we're going to assume that this happens, kind of right away. So we'll say our epsilon SH load equals 1/3 of what we found above, our epsilon SH 6 months. So this will be 165 microstrain. So then we'll have our load age factor. So we'll say our loading age, we'll say is 1/3 of 1/3 of our 6 months, which will be 61 days. So we'll need to find our load age factor, which if we plug in our 61 days, we'll have our load age factor of 0.77. So then our ultimate is 2.35 times our creep factors, which will be, we need to include the volume to surface area factor. So remember, VS in this case was 0.766. So we'll get our VU to be, or our creep coefficient to be 1.39. And then using our time factor, we can find that our time will be 183 minus 61 days to the 0.6 all over 10 plus 183 minus 61 to the 0.6 times 1.39. So this will be 0.891 will be our creep coefficient for this loading. So then we can find our effective concrete modular ratio. So our E effective 3 is going to be EC over 1 plus C3. So we'll call that 3. And this will be 1900 6 KSI. Our eta prime 3 is then 15.2, and our A transformed 3 will be 288.9, square inches. And I would suggest, taking a look at this and seeing if you can get those numbers yourself. So then we can find our concrete stress due to shrinkage using the expressions we derived earlier in class. So we'll have negative shrinkage strain times steel modulus times steel area over our A transformed 3. And if we plug in these numbers, we'll get, negative 497 microstrain times the modulus 29,000 times our steel area, which is 2% of the total area. And then we divide by our transformed area, which was 288.9 square inches. Alright, so then we find that our stress here is negative 0.224 KSI. This is a tensile stress. Alright, so next, we're almost there. Add up all of our components. Alright, so if we add up all the components, then we have our FC 6 months equals our FC1 plus FC2 plus FCSH. And this will give us a stress of 0.254 plus 0.206 plus a negative 0.224, which will be 0.236 KSI. So we can find our steel stress equal to the loading on the column minus FC AC all over AS. So this will be 75 kips plus 60 kips minus 0.236 times 15 squared all over 2%. And this will give us a steel stress of 18.2 KSI. Alright, and then finally, we were looking for the deflection. So we need the steel strain. So our steel strain is then just our Fs over Es equal to 18.2 KSI over 29,000 KSI, which is 628 microstrain. And then we can take this times our total, so our total delta L column is then equal to our ES times the length of our column. So this will be 628 microstrain times the length of our column, which was 12 feet, times 12 inches per foot to convert it. And this will give us a underwhelming deflection of 0.09 inches. So anyway, a lot of work for about 0.1 inch of deformation. So anyway, I'm sure you'll have questions, so we can talk about this again in class on I guess on next Tuesday. Next time we see each other. But feel free to email me any other questions, and feel free to go back over the video. I'll leave it up for a week or two so you guys can revisit it. All right, thank you.